Let us now discuss Gay-Lussac's law. What does Gay-Lussac's law state? For a fixed amount of gas at constant volume, the pressure of a gas is proportional or directly proportional to its Kelvin temperature. That tells us that if the temperature is increasing, the pressure will have to increase, and that's because the molecules will now move faster due to increased kinetic energy, increasing collisions of the gas molecules with themselves and the inner wall of the container, pushing the inner wall of the container outwards. That is force per unit area, that is pressure. Dividing the pressure by temperature will give us a constant K. Again, I'll take you back to the ideal gas law, which is the mother of all these gas laws. Pressure times volume equals to the number of moles times gas constant times temperature in Kelvin. So the Gay-Lussac's law talks about a fixed amount of gas. So here N is constant at a constant volume. So amount of gas and volume is not changing. Volume is constant. The pressure of a gas is proportional to its Kelvin temperature. Okay, so R is a constant anyway. Usually it's 0.08206. So what you are varying, the variables, let's write here, the variables here are pressure and temperature, T. So pressure and temperature are variables. So I can divide both sides by T. I'll get PT equals to NR. Then I can keep it the way it is and then divide both sides by V. To cancel the V from the left side, it comes here. So all these right here are constants. Then N, the V, and the R. So P over T equals to K, which is what this is. That tells you for whichever ratio of pressure and temperature adjustments that you have, the answer should always be the same. And therefore, this leads us to get this formula. Initial pressure 1 in atmospheres or pascals divided by initial temperature 1 in Kelvin scale must be equal to final pressure 2 divided by final temperature 2. Now, knowing any of these three will give you the fourth unknown variable. So the equation I just wrote is this, giving you the initial conditions and final conditions. But let's describe this image here illustrating Gay-Lussac's law. Increasing the temperature will increase the kinetic energy of the gas particles, causing the pressure exerted by gas particles to increase. That is very true. If we are saying P over T equals to K, multiply T both sides, you get P equals to K times T. Okay, and that tells you that P is directly proportional to temperature. Increase in temperature will lead to increase in pressure in the container. So you are looking here, the number of molecules in there, N equals to 8 blue balls. In here still N equals to 8 blue balls. So like I told you, N is constant. And then the volume is kept constant in these two experiments or runs. So V is constant. What we are changing here is the temperature that in turn affects the pressure. So you can see the temperature starts off at 200 and they increased the temperature to 400. We started off with 1 atm at 200 kelvins. Adjusting the temperature to 400, the pressure went up to 2 atmospheres. The piston did not move, so volume is constant. The piston did not move upward or downward. Volume is constant. Okay? So you can focus on the molecules themselves. These molecules are just almost not moving so much. But once the temperature is increased to 400 K, the image shows that we have a trail or a drag of the motion of the molecules, meaning they are moving so much. They gain kinetic energy after the increase in temperature and move so much. Okay, so now knowing that P over T is always a constant, again, we can have this relationship of 4 variables. And if we know any 3 of these, for example, if you're looking for P1, you will be given T1, P2, T2, and you can find P1 or otherwise. So now let's do some examples using this equation on Guy-Lussac's law. Equation is here. It reads, a sample of gas is at 100 kilopascals and 27 degrees Celsius. So I'm given P1, initial pressure is 100 kilopascals, and then initial temperature I'm given 27 degrees. And then it goes on, calculate the pressure if the temperature is changed to 127. So T2 is changed to 127 degrees Celsius, and it's telling us to calculate the pressure. P2, we don't know, that's needed. While the volume remains constant. Well, we know that volume is constant for Guy-Lussac's law, and the number of moles is constant. So what I'll firstly do, I would convert the degrees Celsius to Kelvin by adding 273. This becomes 300.15 Kelvin. So I'll do the same thing for T2, 273.15, and that becomes 400.15 Kelvin. I know that initial pressure over initial temperature must be equal to final pressure over final temperature. Why? The reason is P over T is a constant K. So regardless of the ratio, the answer should always be the same. Okay, so since I'm looking for P2, I can rewrite it like this. P2 over T2 equals to P1 over T1. And then I go ahead and get rid of T2 by multiplying it on both sides. T2 and T2 will cancel, so P2 will be equal to P1 over T1 times T2. My P1 is 100 kilopascals. My T2 is 400.15 K. I'm dividing that by T1, which is 300.15 K. Then I know that I can get rid of the K and do the math. Our answer should read something kilopascals, and we're going to report it to the correct sig figs. Let's do the math. So I have 100, of course, divided by 300. You know, that's gonna be 0.333. And then I'll multiply that by 400.15, and the answer I'm getting is 133.383 kilopascals. Looking at my question, I mostly see that I have 3 significant figures as the least values reported, so 133 would be enough, because if I look at the 3 is less than 5. I don't need to round this 3, so the final answer is 133 kilopascals as the after pressure when the temperature is going to be raised to 127. So you see at 27 degrees the pressure is 100. At 127 degrees, the pressure is 133. So yeah, increase in temperature leads to increase in pressure according to Guy-Lussac's law. Let's do another example on Guy-Lussac's law. The temperature of 200 atm of a gas originally at standard temperature and pressure is changed to negative 25 degrees Celsius at constant volume. Calculate the pressure of the gas in atms. So I know that I'm given P1 to be 200 atmospheres. The hidden information here is STP. STP simply stands for standard temperature and pressure. So at standard temp, that should be 0 degrees Celsius. Okay, so I can tell myself T1 is 0 degrees Celsius. And then it says the temperature was changed to negative 25. So T2 is going to be negative 25 degrees Celsius. We are asked to calculate the pressure of the gas in atmospheres. So P2 is needed. That's what we need to look for. We are not given. So the first thing I should do is to convert the degrees Celsius temperature to Kelvin by adding 273.15. Going to give me the answer in Kelvin, so it will be 273.15 K for T1. For T2, I do the same thing. I add 273.15. It's gonna give me the answer in K. Let's see what that is. 273.15 minus 25. So it's 248.15 K. I know that P1 over T1 must always be equal to P2 over T2. I'm looking for the after pressure P2. So again, to make things easy, I'll just rewrite it the other way around, starting with P2 T2, then P1 T1. Then I'll multiply both sides by T2, like we did before, get rid of T2. So final pressure P2 is going to be equal to initial pressure P1 divided by initial temperature T1 in Kelvin times final temperature T2 in Kelvin. P1 is given as 200 atms. T2 is 248.15 Kelvin, and then T1 is 273.15 Kelvin. So doing so, the K and the K will go, and we do the math. Let's see what we'll get. The answer I'm getting is 181.695 atms. So this is gonna be reported to 182 atms. Now let's inspect and make sure everything makes sense. So at 200 atms, the temperature was 0 degrees. The standard temperature is 0 degrees. STP. And then at 182 atm, our answer, the temperature is negative 25. That makes sense because we dropped the temperature. Decrease in temperature must be followed by decrease in pressure. The pressure decreased. Our answer is 182.